Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, our next talk is a paper by Igor Mordat, Kendall Lowry, Gaten Andrew, Zoran Popovic, and Emmanuel Todorov. Is about interactive control of diverse complex characters with neural networks.
Thank you very much. Yes, thank you for the introduction. As I've said, I'll talk about interactive control of complex characters. And in general, the problem that we're going to be tackling is to synthesize complex movement from simple goals. And the goal here is, for example, to move the character to a particular location that I'm interactively controlling with a cursor. And different characters might automatically adapt different strategies to satisfy this goal. Strategies from flying, to swimming, to bipedal walking, to quadrupedal walking. And we would like these movement strategies to be discovered fully automatically without the need for manual design or manual specification of motion or engineering. And we don't want them to come out of, say, mimicking of existing motions that we provide. We would like to have them discovered de novo. And being able to do something like this has a host of implications in fields of robotics for autonomous control, of versatile robot platforms, in biomechanics and cognitive science to be able to, say, perform virtual experiments and study the effects of various equipment or prostheses or surgical procedures, and also in computer graphics to be able to automate the animation in films or interactive games. Now, the interactive controllers that I'll talk about in our case are going to be represented by control policies, and you're probably fairly familiar with this topic, but just to make sure we're on the same page, what I mean by a control policy is going to be some function we'll call pi that has some parameters theta that is going to map the state of our agent, for example, like all the joint angles of this bipedal character or the joint angle velocities and the target velocity that you want this character to walk at. And it's going to output some actions, for example, all the individual joint torques applied to the character. And we're going to apply those joint torques, and we're going to end up in a new state. And once again, we can query the policy repeatedly, take a look at the state, the policy will output an action, and if we keep repeating this, we're going to get the behavior of the character that will satisfy the tasks that we want. Now, there's been a lot of research done in finding these control policies. One way you can go about it is to pose it as a general search or optimization problem leading to, say, policy gradient methods and a lot of that work. But in the general case, that is a very difficult optimization problem and has typically been limited to fairly low-dimensional systems and somewhat not particularly complicated behaviors. So the other way you can go about it is to incorporate more of the additional structure if you know something about the behavior. So for example, if you know you're going to be creating walking controllers, you might create some specially designed state machines, or if you're going to be creating swimming creatures, you can possibly express the policy and say a composition of sinusoidal or cyclic functions. But these, again, limit the generality of the approach or of the different platforms that you can apply this method at, and require a lot of manual insight or a lot of human insight. So the way that we're going to try to approach this problem is make use of two approaches, is make use of trajectory optimization and make use of supervised learning. And I think we're all familiar with supervised learning, but I think it would be worth to talk a little bit about trajectory optimization and either introduce or review it. So in trajectory optimization, for example, let's say you have a character agent character that starts in some initial configuration, let's call it Q0, containing, say, all the joint angles of this character. And it has some tasks that you want this character to achieve. So for example, move the center of mass over the ledge. And as what we'd like to have is find a motion that satisfies this high-level task. And the parameters of the problem that we're going to be optimizing over is going to be a collection of these poses of the character from time 0 to t, and also in addition, the contact forces that this character applies to the environment and vice versa. And this optimization is going to be subjected to some constraints, such as the kinematic constraints, say making sure that the elbows don't bend backward and all the joint limits of the character are satisfied. Also the dynamics constraints, making sure that the transition between any two poses, Q1, say Q1 to Q2, obeys the laws of physics. And also some additional contact constraints that will enforce consistency between poses and forces. I don't want to go into too many details of this. For more details, you can find me at the poster. But then, basically, we can impose these constraints. In our case, we impose them as soft constraints and just fold them as additional objectives. And the resulting problem can be solved with standard existing local gradient-based optimization methods. In our case, we use Gauss-Newton method to solve all of these problems. And as a result, what you can get is actually, we've done a lot of work on this, and in particular, after very careful treatment of contact, we're able to find optimized trajectories that solved very, very complex movement problems. Again, without any particular clever initialization or any additional input, just from few high-level goals like where the final location of the character should be. But for each of these movements that you see, it's only specific to a particular situation where the character starts at a particular initial state and has a particular goal. But what we're after is learning policies that are applicable everywhere, not just for one situation. So what's one way that we can think about going about learning these policies? Well, one initial thought that you can have is we're going to pose a collection of problems, say 1 to n, and a collection of situations. And each of these situations, we're going to find an optimal trajectory using the methods that I've just talked about, find a solution, find a motion. So for example, character walking backward 1 meter, or say another task where the character is walking forward 2 meters. And we're going to collect state and action pairs from all of these solved trajectories. And we're going to use our favorite function approximators, such as a neural network, for example, to fit a general mapping from states to actions. And hopefully that approximator will generalize to unseen cases, like walking backwards 1.5 meter, or something like that. So the problem with this is that this collection of trajectories, this x1 to xn, can be a very difficult or even an inconsistent data set to learn, and that's what we found in practice. Like, this approach did not work well because, so for example, there are many ways to walk forward 1 meter. You might, like, say, start with the left foot, or you might start with the right foot. And some trajectories might be doing it with one way, or some trajectories might be doing it with the other. And if you're trying to fit a single for a particular state, you're trying to fit a deterministic or a unimodal policy, then it's going to try to do something in between, stepping with the right and stepping with the left, and that's not a particular sensible strategy. So what the strategies that we're proposing instead is making sure that the policy that we're learning actually feeds back into the trajectory optimization problems. And so one way that this can be posed is, if you think of the problem jointly optimizing, say, policy parameters and this collection of trajectories, where the objective is that each of the trajectories must be satisfying those goals, like getting to a particular location while satisfying laws of physics, but also have an additional term that says, well, the actions along each of the trajectories have to be what our policy would output along the states of that trajectory. So you basically have this additional term that says trajectories have to stay close to the policy. And in practice, of course, like this is a very large optimization problem, and we can decompose it into a collection of independent trajectory optimization problems, holding the policy fixed, but just having this additional quadratic term. And then we simply use regression on the fixed collection of state and action pairs from the policies. And if we keep alternating this, we actually end up observing convergence where the policy actually ends up being able to reconstruct these trajectories that we observe. And one very nice thing is that this can be done in a distributed and very scalable way. So in practice, we can actually have this very large collection of trajectories running on a cluster of machines where each machine is, for example, responsible for asynchronously optimizing some trajectories, sending the data to another machine which does supervised learning with existing neural network implementations. And you never actually need to put the entire data set into memory. The data set can actually change. We can add new trajectories or new tasks on the fly or remove them as necessary. So I think we've only begun to explore the future possibilities of this, but I think that is a very exciting aspect of this approach. And just to be a bit more concrete than our implementation, the policy, as I said, we're going to be using neural networks, although other function approximators could potentially be used. And as an input, we're going to take, as I've said, the join angles of the character and the contact forces. And the policy is going to output how these quantities change. So it's going to output how the join angles and forces change. So one interesting aspect of this is that it ends up learning a model of the dynamics under the optimal controls. And it can possibly be used to make predictions of what the future will look like without ever invoking a simulator, so imagining how you would move like in the future. And so this is one example of me interactively controlling the target, and you see that what is a collection of those poses is trajectories predicted without ever touching the simulator. And another aspect that we found to be very important in making this work is injecting noise to make this training robust. So one issue is that, or something that you would have to encounter is policies, if you're just training them on this collection of trajectories, they may not be exposed to what they should do around the trajectory states. So for example, if I'm at a state S, I'm not sure if you can see it here, I'm at a state S and I know what to do there, but if I suddenly deviate or drift to another new state or nearby, S plus epsilon, I need to be able to make an adjustment on what to do in that nearby state. And we have, I don't want to go into the details of this, but if you assume that this correction to the action is going to be linear, you can very efficiently calculate for what the action should be in this corrupted or noisy state. And this idea is, I guess, somewhat similar to denoising autoencoders that Yoshio talked about at the tutorial yesterday. But here the task is different. Instead of corrupting the input and trying to reconstruct the original version of the output, here you're corrupting the input, but it also induces a particular change in the output that is not just being able to recreate the original. And we've also found it important to also add noise into the neural network training itself. So for example, we could have used dropout. We've used additive noise to the units instead. And just to show you what would happen if you were to try to optimize policies without using this noise, you can see the tasks kind of end up being successful sometimes, but they're very, very like meandering. And when you do this policy optimization with noise, the task always ends up succeeding very, very quickly. So because it knows what to do around nearby states. And this is kind of what it looks like for a very small data set that we're learning on. Training without noise can kind of meander, but training with noise ends up succeeding really quickly. And now to show you some examples of what we're able to do and talk more about them in detail. In this case, we basically have a collection of boxes essentially actuated by some motors at the joints, and the air has a particular medium, in this case, that of air. And we're not assuming anything else. We're not, for example, assuming that these joints are actuated by cyclic state machines or a collection of sinusoids. What's driving this behavior is just entirely a general four-layer neural network that was trained with this with our algorithm, and it's able to achieve the tasks such as moving backward and forward. And when then using the same neural network architecture, using exactly the same algorithm, what we can do is just build another character and change the environment so that the medium is that of water, which is quite a bit denser. And we can get very different behavior strategies coming out without doing any manual changes. And we can control not just, say, the location, but also the heading. And that is incorporated as an input into the network. And again, using exactly the same network and architecture, we can set up a humanoid that is able to contact with the ground and has access to those ground reaction forces, which is how it actually ends up locomoting. And again, there's no motion capture or anything being used. The trajectory optimization discovers that to move forward, you need to make a series of motions that looks like a footstep. And then the policy ends up learning and generalizing that. You can also try to have different morphologies, such as this slightly shorter character or this much, much wider character that still finds strategies to move. And also quadrupedal characters to both get to a particular location and also turn around. Or various spider-like creatures. And one thing I should say is that the resulting policies are also very coherent. So as I've showed before, as you change the target location, you're not getting very wildly different strategies. So you can have some confidence that these resulting motions that the policy is going to roll out are going to be reliable and they're not going to do something unexpected, which is good for safety. We can also incorporate additional sources of information, for example, like sensors, like kind of a foveal field around this quadcopter that says how close am I to the obstacle, and get policies that move to avoid obstacles. We've also briefly tried implementing this on physical robots, where we're only working with the sensory information that's available to the robot and not any additional sources. And here, the goal is to get the torso to a particular orientation that is controlled by my co-author's mouse cursor. And there isn't anything, for example, we're not making use of, say, end effector or Jacobian transpose control or any of those ideas. These is learned just coming out automatically. And here the goal is to, for example, move the end effector of the hand to a particular location that is, once again, controlled interactively by the cursor. We'd like to be able to try locomotion behaviors. Unfortunately, all the policies we've tried to do require access to contact forces, and we've just only put in the contact force sensors onto the robot, so we're really excited to try to do locomotion next. So to conclude, we have been able to find a method to automatically discover policies for movement behaviors with a very scalable implementation that can distribute the workload across machines. We're only using 40 machines so far, but we can potentially scale it up to a much larger number. And it didn't require any manual policy, manual design of policy structure or any initialization for the motions. And in the future, we'd like to be able to transfer the work across domains, in particular, do more work on applying this in the physical world, study how sensors affect the behavior, and use more just rich sensory information such as visual input. So thank you.
probably time for one question. Could the spotlight speakers
there we
come
go.
up, please? Thanks.
Yeah, so this reminded me a lot of guided policy search in the sense that you're kind of finding some optimal trajectories and then trying to learn a neural net that can reproduce them. Can you just briefly compare and contrast?
Yeah, in fact, this work was kind of going on in parallel with guided policy search, but I think there's a lot of similarity, and that is really great work. I think one of the differences in practice ends up being that we use a particular trajectory optimization method that is quite a bit, I think, is able to find strategies for movements that involve a lot of contact, and that allows us to try to get at the motions that the other method was not able to do before. But I think in general, there's a lot of similarity between the two approaches. Also, with regards to scalable distributed implementation, I think there are some things with guided policy search that making use of a DMM makes it not entirely obvious how to implement that, but there are potentially ways. So, yeah.
Thanks.
Great. Let's thank the speaker again. Thank you.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.